Hello everyone. In this video, we will be using Leibniz theorem to solve a problem, and our problem is we are given y equals e to the power a times tan inverse x, and we are supposed to prove these two expressions. We are supposed to prove these two expressions. So for first expression, what we can do is, so we have y equals e to the power a tan inverse x. Now differentiate this equation 1 with respect to x. So the derivative of y is written as y1. So to find the derivative of this term, we can use the chain rule. D e to the power a tan inverse x over d a tan inverse x times d a tan inverse x over dx. So this is similar to d e to the power x over dx. So the derivative of e to the power x is just e to the power x. So you can write e to the power a tan inverse x. And here, since a is a constant term, we can move it out of the derivative operator. So we will get a times, and the derivative of tan inverse x is 1 over 1 plus x square, and we have y1 here. Now move 1 plus x square to this side. We will get 1 plus x square y1 equals to a e to the power a tan inverse x. In next step, we have 1 plus x square y1 equals a. If you notice, e to the power a tan inverse x is y, so we can replace this term with y. Now to prove this, what we can do is, we have y2 here, meaning that we have to differentiate y 2 times with respect to x. We have already done it one time, so we have to differentiate this expression again one more time with respect to x. So I'll make it as equation 2. So differentiating equation 2 with respect to x, we get use product rule here. So keeping 1 plus x square as it is, the derivative of y1 will be y2 plus, now keeping y1 as it is, the derivative of 1 plus x square will be just 2x, and since a is a constant, we can just write it as a, and the derivative of y will be y1. So we have 1 plus x square y2, we got the first term, plus bring this term to this side, we will get 2x y1 minus ay1 equals 0. Now take y1 as common, we will get 2x minus a y1 equals to 0, which completes our proof for this first expression. Now to prove the second expression, we will need to use this expression. Now here we will be using the Leibniz theorem. Using Leibniz theorem, differentiate third n times with respect to x. So the step is, keep 1 plus x square as it is, 1 plus x square as it is, and since we have y2 here, write y n plus 2, and plus in next step write 1 c n c 1, and we have n plus 2 here, so reduce it by 1, we will get y n plus 1, and the derivative of this term will be just 2x, plus we wrote n c1. Now we'll write n c2 and again reduce this term by 1. So we'll get y n and the derivative of this term will be just 2. See that we have reached to yn, so we don't need to move further. Just write plus and proceed for this term. Now similar to this part, keep 2x minus a as it is, 2x minus a as it is, and since we have y1, write yn plus 1, again plus. Now again nc1, reduce this term by 1, yn, and then the derivative of 2x minus a is just 2. We have 1 plus x square yn plus 2 plus nc1 is just n yn plus 1 and 2x plus nc2 is n times n minus 1 by 2, but this 2 and this 2 will cancel, so we can just write n times n minus 1 and yn plus 2x minus a yn plus 1 plus nc1 is n, we have yn and 2 equals 0. Now we have 1 plus x square yn plus 2. We got the first term. So for second term, group the terms having yn plus 1 yn plus 1. So we have yn plus 1 here and here. So group it. So take yn plus 1 common from these two terms. We get 2nx from this term plus 2x minus a from this term, and we have yn plus 1. Now plus, now what we can do is open this bracket. We will get n square yn minus nyn plus 2n yn equals to 0. 1 plus x square yn plus 2 plus 2nx plus 2x minus a yn plus 1 plus 2nyn minus nyn is just nyn. So we are left with plus nyn. 1 plus x square yn plus 2 plus 2nx plus 2x minus a yn plus 1. Now take nyn common from this term. We will get nyn. So we are left with n plus 1. So we can rearrange this like this, which also completes our proof for the second expression. Thank you.